Okay, so we talked a bit about mechanical, reviewed those a bit, and now we're going to go on to electrical integration. And I have some notes here. And oh no, I just closed my window rather than opening it. No. So in your in the Moodle shell, there are a couple of exercises that deal, well, a couple of examples that deal with wire sizing and so forth, and they're based on this module. It's Evergreen Solar, and they were around years ago, and they had a slightly different technology than most of the manufacturers now. They, I believe, went bankrupt and sold to a different company, and I don't even know if they're still in manufacture or being manufactured, but the gist is that the electrical characteristics that you see on this spec sheet are going to be the same as pretty much anything you look at. And I have a couple of other examples of module spec sheets, and we'll go back and we can look at those. And then you guys can go through this one. I think it's a good one because it's fairly simple in terms of the it being pretty readable. So if you have questions, if you've had time to review the material, we can go specifically into evergreens if you want, but I'll pull up some others. So some of the keys with the electrical are basically what we're doing is looking at the requirements of the different components, such as the inverters, what we need for voltage, what their maximum power output or tolerance is, what our wire sizing is based on those parameters as well, the voltage and the current, and then we also go into grounding the system and other aspects. And this one is right up top here. So this, we talked a little about the mechanical side and how there's issue with galvanic corrosion if you have a copper wire laying across an aluminum rack or something of that sort. And so this table, which I can get to Brad and put up if you guys are interested, or you can find something similar online, it just tells you the tendency of different metals to interact or to react with one another to give you corrosion. And so it's useful both when you're looking at the mechanical as well as the electrical side, because if you have an aluminum wire for whatever reason and you want to connect it to a copper, then that can be a big issue, and you'll need some special treatment to make that connection. And you can see aluminum is up here near the top, and it tends to be a better anode, and copper is down here toward the bottom, which tends to be a better cathode. And so there you get the tendency for those two to react with one another. And then if you have metals that are close to each other, they're going to be less likely to react with one another. So, yeah, and I don't know if this table has iron. I was just looking for stainless steel to see how it compares with aluminum, but anyway, that's just kind of a side note. when we start looking at let me go and open an inverter cut sheet. So this is an older inverter. I think most of these are older, but when we're doing a grid-tied system, we're going to size the system based on a couple of things. One, we're going to look at what the energy consumption is. You know, how much power, how large how large the array needs to be or can be. We don't want to oversize the array and produce more than the house is going to use. If we do, we're basically giving power away, and most people don't want to do that. So then the other element, once we figure out, okay, so we know how much we want to produce, we can figure out the array size, and it may be limited by roof space, so that might dictate a smaller array, or it might be affected by affordability. You know, how much money do people have to spend? I may say, well, I'd really like to do 5 kW, but we can only afford a 3 kW system, and so then that'll kind of get you, those might dictate how large the components can be. So you figure out your
system,
and just talking about a grid-tied system right now. And so this is a grid-tied inverter, and you might say, okay, so we can fit about 3 kW on the roof. They might want more, but that's all the space we have to use, and so we'll go and look at the 3 kW. And when we look at the specs on this, you can see the recommended PV power, and it might, and often the PV rating, the PV power will be higher than the inverter because of the efficiencies, and 3 kW of solar modules is occasionally going to produce more than 3 kW, but for the most part it's going to produce less. So so that's why you'll often see the higher rating on the PV modules. But from the electrical perspective, you're going to come down and you're going to see here we have a maximum DC voltage, and we also have a minimum or a start voltage for the inverter. And so we have to pay attention to those, because when we start building an array, we're going to plug modules into each other, and we're going to put them in series. So if your modules, let's go and open one of our module specs, and I'm going to pull, let's see, we've got Evergreen here, Fronius, our size, electrical modules. So I've used REC quite a bit, and I like them because they refine their silicon and butte, even though the bulk of the work is done in Singapore or who knows where else, but at least there's some tie to Missoula, and I think they're a good quality manufacturer. And so here we have electrical characteristics on this module, and you guys talked about modules before earlier in the class, and so I'm expecting you have some familiarity with the parameters, the max voltage, the max power voltage, and things like that. So what we'd look at is we want to think on the inverter there was a minimum voltage or a start voltage, and so if the modules, if your array voltage is less than that, then the inverter simply doesn't turn on. So we could figure out how many of these modules it would be required to regularly meet that start voltage. And so we have the open circuit voltage, let's say the 250 watt module, which is the third one over, and that's 37.4 volts. And then if we go back over to our inverter, we see our minimum voltage, or the start voltage, for a 240 is going to be let's see, let's call it 200 volts. So how many modules do we need in series to start that inverter on a regular basis? If we divide 200 by 37.4, oh, did I do something wrong here?
200.
200 divided by 4. Did I do times?
I do that so often.
200, let me take my time, divided by 37.4. And so 6 modules would be the minimum, and then we have to think about other aspects.
So 200 volts was what the module puts out.
No, the inverter needs to kick on.
Yeah.
One module is 37. Okay.
Yeah, each module's, I think that was the open circuit voltage.
Can you list that voltage? Is that like the voltage at the solar constant, or is it?
No, so that's the voltage before the inverter engages, before it's open circuit. So you've just got the sun shining on the modules, and there's no load on the array at all. So, and then that's the other thing, to know whether the inverter, yes, it will come on at 200 volts, but is it going to maintain, and what's going to happen to your max power voltage? What's going to happen to your voltage once it does engage? And is that going to run the inverter? So there's some little things, and a lot of that might depend on the nuances of the individual inverters. So I would say it's always good to overshoot that low number for a couple of reasons. One, because you want to make sure that once the inverter engages and you have load on the array, that the inverter continues to run when your voltage drops. Two, you're going to see lower than normal voltages in the summer. When the temperature's higher, those modules are hot, they're going to be producing a lower voltage, because the voltages we're looking at on the spec sheet are, yeah, so these are standard test conditions. So that's going to be affected a great deal if the module's in the hot sun on an afternoon and you've got a little blip in the power and the thing goes offline and then it tries to come back online. Your voltage might not make that window because of the temperature effect. So when we're figuring out the low voltage, we want to look at what the inverter is going to require if we can figure it out. If not, safer would be, as you pointed out, to use the max power voltage rather than simply the open circuit voltage. And then also to look at, okay, let's say temperature effects, max power voltage. What else? I had another in mind. Oh, a blank. But you need to factor those in as you're determining what the smallest possible array you could put with an inverter. And so this inverter, you could put a couple of strings, but you wouldn't want to, have fewer than your minimum limit to make it operate. Oh, the other thing I was going to say is degradation. As panels degrade over time, you expect about a 1% voltage drop per year over the life of the panel. So you might put it in this year, and even the hottest summer day, it works fine, but 10 years down the road, it might be a different story. So
Is that like a kind of 1% a year? That's kind of what to expect, or worse.
yeah.
And you don't
Well,
mess with
most, and that's another of the parameters of the modules, I think their warranty is a separate sheet, these guys. So let me pull up.
I saw something 10 to 25 years at the bottom of that sheet.
They have a guarantee of like
Something
720
26 or 10 to 25.
This one's pretty good. Uh-oh. Swinging the screen there. Let's see. Series poly. So, Solar World is really proud of their warranty. I say that, but now I can't find it. Let's see. And so here's their they have a 30-year linear performance guarantee, and they're saying 30 years out it's gonna still produce about 87%. So they're guessing less degradation than 1% per year. So like a 0.5% per year. But on the safe side, if you use 1% per year, then you can have a good sense of what your safe voltage is going to be 10, 15, 20 years out. So, and again, this is just another module manufactured, different selling features. They're going to tell you all this different stuff, but standard in the industry is going to be your table here that's going to give you your max power output at standard test conditions, and then also at NOCT, which is going to be, NOCT is more real world type expectations. So, and then typically they'll include all the spec data, but what you're going to be interested in is when you're looking at the electrical characteristics, you're going to be interested in the open circuit voltage, the max power voltage, short circuit current, and max power current, because those are going to be the things that affect how you design a system, how you size the array with the inverter, both of those components, as well as wire sizing, which is a whole nother game, and we'll look at that a little bit here. So let's see. Let's see how we're doing on time on the... Yeah, maybe we can stop for a second and I'll pull up the wire sizing and then we can jump back into it. So we'll be right back.